Our next problem is another one which is concerned with bacteria, but here we're given the data in a different form, there's a different story that goes with this, and we'll have to work with what we've got. A population of bacteria is growing under ideal laboratory conditions. Thus the population is growing exponentially. Suppose that after 4 hours there are 5,000 bacteria, while after 12 hours there are 10,000 bacteria. How many bacteria cells were present initially? So we're solving for P0, and we're given P of t at 2 different times. So let's write down that information. We're told that it's an exponential model. We want P of 0. P of 4 is P0 e to the 4k, and that's 5,000. That's given to us. And P of 12 is P0 e to the 12k, and that's 10,000. That's given to us. So now we have 2 equations in 2 unknowns. It's P0 that we want, and the other unknown is k. And because it's in the exponent, it generally will happen that we have to find that exponent first before we get to P0. So how can we do this? Well, my preferred way of doing this one is to divide the first equation into the second equation. That will cancel out the P0s, and that'll let me solve for k here. So what does that look like? Well, when we divide P0, the P0s cancel out. E to the 12k divided by e to the 4k is e to the 12k minus 4k. You subtract the exponents when you divide. And 10,000 divided by 5,000 is just 2. So if I subtract, I get e to the 8k equals 2. Now from here, we can go off in quite a few different directions to find the ultimate solution of this problem. We could solve for k or for e to the k. There's a variety of things that we could do. But what I'm going to do is to solve for e to the 4k, because that will let me just divide it into 5,000 and get P0 up there. So we know that e to the 8k is equal to 2. Let's take the square root of each side of that equation. The square root of e to the 8k is the same thing as e to the 8k raised to the power 1/2. And 1/2 of 8 is 4, so I get e to the 4k. The square root of 2 is just the square root of 2. So e to the 4k is the square root of 2. We know that P0 e to the 4k is 5,000. So P of 0 is 5,000 over root 2. So that's 3,535 bacteria. So we've solved the problem now. We could have solved this by looking for k, by taking the logarithms right there. In fact, back in our initial equations, we could have solved this problem by cubing both of these numbers and then eliminating the e to the 12. So there's a variety of ways you can do that. The point is that in the first part of the solution, we have written down the information that was given to us in the question, including the exponential model and then the other data which is given to us. From that point on, you're not doing calculus or modeling, you're doing algebra and theory of functions. You're just using your skills at solving systems of equations. So if you have that bound up in a different part of your brain, you should open up that particular cupboard and get all those skills out, because you're going to need them to solve these problems. Okay, let's just summarize what we've got so far. In this video, we've looked at the general solution of the differential equation y prime equals ky, and we discovered that it's p of t equals p of 0 e to the kt. There are 4 quantities, and any one of them can be the unknown in a problem. There are many examples of exponential models that are used in many different disciplines, and I haven't mentioned it, but in fact it's a key part of understanding the climate change models. And facility with working with exponential equations is going to be a strong asset for you in dealing with these problems. And as a final note, there are 2 further videos in the series. Exponential Models 2 will look at radioactive decay problems, so that's half-life and doubling time models. And Exponential Models 3 will do some examples of financial models and Newton cooling. So I'll see you for those videos.